So here we're going to give an example of how to calculate pressure inside of Earth, though really you can use this to calculate atmospheric pressure on a mountaintop or in a deep valley. The basic equation is that pressure is equal to rho g h. So h is the height of whatever it is we're looking at, or it could be depth inside of Earth. So we'll be looking at that in a moment. And then g is the acceleration due to gravity. And then rho is the very common Greek symbol that we use to abbreviate density. So the pressure of a system will be equal to the density of the material, the acceleration due to gravity, which for us will be constant, though if we're looking at pressures on Mars or the moon, or very, very deep in the Earth where gravity changes a bit, then gravity would not be a constant, could be different. And then h is the height of the material or the depth of the material that's pushing down on whatever we're interested in. So let's take a look at this case here. Let's say we are standing here at the surface of the Earth. So here's the solid Earth down here, and we want to know what is the pressure at this depth here, and we'll let that depth, h, be 30 kilometers. So what would be the depth at 30 kilometers? Let's say that this material has a density of 2.8 grams per cubic centimeter. That's a little bit light probably for something that is that deep. So we've got some very thick continental crust in this example that I've made up here. So what would be the pressure? Well, let's erase the chalkboard to give us a little bit more room. The pressure would be equal to, well, we're going to have to do a conversion. We have density as 2.8 grams per cubic centimeters. So we're going to convert that into kilograms per cubic meter. So that'll be 2,800 kilograms per cubic meter. So if pressure is equal to rho gh, then we would have pressure is equal to 2,800 kilograms per cubic meter, and then g will be 9.8 meters per second squared. And again, using meters, too early for the equals sign. We said we have a depth of 30 kilometers, and so that would be equal to 30,000 meters. And so then this whole thing will equal to 8.23 times 10 to the 8 kilograms per meter per second when we cancel out the various units here. And what does that give us? Well, this is equal to pascals. 1 Pascal is, remember one from another video, 1 Pascal is equal to 1 Newton per meter squared. And so that's what we have in a different form of units when we're expressing newtons in terms of kilograms. So we have this many, this is equal to 8.23 times 10 to the 8 pascals. Let's put that into more conventional units. So I'll erase the chalkboard. If we have 8.23 times 10 to the 8 pascals, this would be equal to 8.23 times 10 to the 0. Well, we don't really need that. That's just 1. This would be 8.23 kilobars, or 0.823 gigapascals, right? We get gigapascals by taking these in billions at a time, so we divide by 10 to the 9th. If we divide by 10 to the 9th, that's just moving the decimal out here. Another common unit in geology is megapascals, and so this would be equal to 823 megapascals. So all these things are equal. Let's get rid of this stuff here. This 8 times 10 to the 8 pascals would be the same as 8 kilobars, or 0.823 gigapascals, or 823 megapascals. Now, just to finish up this video, what if we have different densities? So what if we have, here we are standing on Earth's surface, What if we have an upper layer here that is at 2.8 grams per cubic centimeter, but let's say below we have a mantle that is, and we'll just put it in some other kind of dashed notation form. Let's say that has a density of 3.3 grams per cubic centimeters. And let's say we still want to know the depth here, the pressure at the depth of 30 kilometers, but let's say this boundary is at, let's say, 10 kilometers. I'm not really drawing it to scale, but let's say we have 10 kilometers of crust and then 20 kilometers of mantle with two different densities. Well, pressure is additive. That total pressure would be rho GH at 10 kilometers plus rho GH at the next 20 kilometer interval. So the total pressure would be equal to 2,800 kilograms per meter cubed multiplied by 9.8 meters per second squared multiplied by 10,000 meters. And then we would add to that 3,300 kilograms per meter cubed multiplied again by 9.8 meters per second squared, and then multiplied out by 20,000 meters. So if we add those together, then we get the sum of the pressure, those two pressures. What we're doing is effectively calculating the pressure here. So at this 10 kilometer layer there, that's this first part of the sum. And then if there were no pressure at all, if this were the surface here, this second part, this second term would give us the pressure of this layer, and then the total pressure at 30 kilometers would simply be adding those two together. And we can do this for as many layers as we like. We can have 4, 5, 6 layers. We would just add up the pressure for each individual layer, and then that would give us the total pressure at any depth we are interested in.